Number 1 says, for an experiment, a scientist designs a can that's 20 centimeters in height that can hold water. A tube is installed at the bottom of the can, allowing water to drain out. At the beginning of the experiment, the can is full. When the experiment starts, the water begins to drain, and the height of the water of the can decreases by a factor of 1/3 each minute. Explain why the height of the water in a can is a function of time. And so we know that something is a function when each input has exactly one output. And so in this case, the input is time. So for each period of time or each time measurement, there is exactly one height, or there is a unique height. There is a definitive value for the height. So meaning if you look at the times at 3 minutes, it's not going to be 10 centimeters and 7 centimeters. So for every minute that you look at, there is a specific height output. For B, it says the height h in centimeters is a function f of time, t minutes, since poking a hole. And so then it's saying h, or the height, equals a function of time. So write an expression for f of t. So f of t, we know that the height started at 20 centimeters. So that's our initial height. And then we know that the growth factor is 1/3. Okay, so it's decreasing by a factor of 1/3 each minute. And then that would be to the t power. And so if we take a look, it says record the value. So we'll use this function for when t is 0, 1, 2, and 3. So if we do this for 0, so when we plug in 0, anything to the 0 power is 1, and you can certainly use your calculator for this, but this will just be 1. So then 20 times 1 is just 20 for that 0. If we plug in 1, so now we're going to get 20 times 1/3 to the 1 power, so just 20 times 1/3. And if we think of multiplying fractions, that's going to be 20 times 1 on the top and 1 times 3 on the bottom. So we get 20/3 for the height there, or you could certainly do the decimal version of 6.6 repeating. For 2 minutes, then we've got 20 times 1/3 squared. And so if we think of 1/3 squared, that's going to be 1 times 1 on top, which is just 1, and 3 times 3, which is 9 on the bottom. And so then if we multiply that out, that's going to be 20/9 after 2 minutes. Or you could, again, certainly have the decimal version of this, which is 2.2 repeating. And then at 3, if we follow this pattern, then we'd have 3 cubed on the bottom, right? So this was 3 to the first on bottom, 3 squared on bottom. So this is going to be 3 cubed on bottom, which is going to be 20/27. Or the decimal version would be 0.74. So again, you can certainly use your calculator. You don't have to do those in your head. D says find f of 4. Okay, so now it's going to be, 3 to the 4th power on bottom. So it's going to be 20/3 to the 4th, which is going to be 20/81, which is a decimal of about 0.25 centimeters. Then it says sketch a graph of f by hand or using graphing technology. So if I just do a quick little sketch here. So we know it started at 20 centimeters. So if I call this 20, and then I'm going to count by 5. So 5, 10, 15, 20. And then we're going to do 1, 2, 3, and 4 minutes. So that first one at 0 was at 20. The first minute, it is down to 6.6 repeating, so just above 5. The the second minute, it was at 2.2. So the second minute, it's down here at 2.2. And then after the third minute, it is at 0.74. And then the fourth minute was 0.25. So it's just getting kind of closer and closer to that x-axis or to 0, which is what part F is asking us. What happens to the level of water in the can as time continues to elapse? So kind of that height. And so as each, minute passes, the water, or the height of the water, is 1/3 of its previous height. So you could say that. You could say the water, the water level gets closer and closer to 0, meaning closer and closer to the x-axis. So closer to the x-axis over time. So however you want to say that, or if you have a different way of saying it, but it's just decreasing, by 1/3 of the previous one, getting closer and closer to 0, or getting closer and closer to that y-axis. Number 2, a scientist measures the height of a tree each month, and M is the number of months since the scientist first measured it. So we've got H for the height, and then M for the number of months since the scientist first measured the height of the tree. Is the height H a function of months? So meaning if we look at M as the input, okay, and H as the output, is this true? And that would be yes, because for each month, so each month has one definitive measurement for the height. So if we look at January and we look at the height, there's a height. February, there's a height. March, there's a height. There's not just going to be two different heights for the same month. Now, is the month a function of the height? Meaning if we look at the height, does the height give us back a specific month? And there's kind of two different options here. So option 1 is that it could be if all of the heights are different. So if we have if we have all different height values, so they never the tree is never the same height in different months. So if there's all different heights, then yes. So theoretically it could be. So this is like one option, okay? But really, for the most part, it's likely no. Because you could have, you could look at a height, because a height could happen in 2 different months or in more than 1 month. And so if we take a look at this, like maybe I'll just draw out a chart here. So if we were to look at this as month versus height. So in January, the height is 15. In February, the height is 16. In March, the height is 17. In April, the height is 18, or whatever we want to say. And you could continue on like that with different values, right? So each month, even if, so then if we did this and then the tree kind of stopped growing for a couple of months, this is still fine because the months are producing a value. So each month gives you back a value. You don't just have the month going to 2 different values. So now in this other case, if we had the height versus the month. So now if we took a look at this exact same case, sure, when it's 15 whatever feet tall, that's in January. When it's 16 feet, that was February. When it's 17 feet, that's March. When it's 18, now we've got all these different values that it goes to. So 18 kicks back, all three of these values. So you don't know which one it goes to. So that means it's not a function. And so if all of these heights happen to be different, sure, okay, but if you had any heights the same, then it wouldn't be. Number 3, a bacteria population is 10,000 and it triples each day. Explain why the bacteria population B is a function of the number of days. So again, same thing, each day there is a specific amount of bacteria or a unique output. Each day produces a unique output. Which variable is the independent variable in this situation? So which one is the one that's changing or not dependent on something else? And that would be the days. Write an equation relating B and D. So the bacteria is a function of the days. The bacteria initially starts at 10,000 bacteria. And then the growth factor is triples. So that's 3 times as many each day. So then we have 10,000 times 3 to the D power. Number 4, is the position P of the minute hand of the clock a function of time? And so where the minute hand is, and maybe I'll draw a clock here. Okay, and so then, you've got the minute clock or the minute hand versus the hour hand. And so now is the position of this minute hand on the clock a function of time? So meaning if we know the time, does that kick back a specific place? And that would be yes. Okay, so for part A, it's yes, because each time equals a specific position. Now for part B, is time a function of the position? And this is no, because the position of the minute hand happens at multiple different times. So if, for instance, we know that the minute hand is here, right? This could happen at 1 o'clock, at 2 o'clock, at 3 o'clock, at 4 o'clock, 5 o'clock. So all these different hours on the hour happen when the minute hand is here. So just because you know the minute hand is here doesn't mean you know where the hour hand is at. So that means, nope, not a function. Number 5, the area covered by a city is 20 square miles. The area grows by a factor of 1.1 each year since it was 20 square miles. Explain why the area covered by the city in square miles is a function of time, which is the number of years since it was 20. And this is again because then each time, which is our independent variable, so each time gives a specific area. So if I tell you 4 years, you'll have an area, a specific area, one area, not multiple different areas, just one. If I want to know what the area was after 7 years, one answer. So then write an equation A in terms of T. So area as a function of time is equal to the initial area, which is 20, times the growth factor, which is 1.1, and then the exponent is your time measurement, so, or your time variable, so in this case, t. Number 6, the graph shows an exponential relationship between x and y. Write an equation representing this relationship. So remember that we're going to need, so in this case, it's x and y. So we'll say y equals, we need the initial value. So we need our initial amount, which happens at x equals 0. The output is our initial value. So that's 50. Then we need to multiply it by the growth factor, and then that'll be raised to the x power. So to find the growth factor, we're going to take a new value divided by the original value, or the one right before it. So we're going to take this one divided by the previous one, so 100 divided by 50. And we see that that's 2 times bigger. So then that's our growth factor. And you can check it to make sure it stays. So you could also look at 200 divided by 100. And that again is a growth factor of 2. So then what is the value of y when x equals -1? So you can do this a couple different ways. You can plug it into your equation here. Okay, so you could just plug it in and use your calculator. Okay, you can also think of, if it's doubling as we move forward, then it's going to be cutting in half or dividing by 2 as we go backwards. So if our initial value was 50, back one growth period would be half of 50, or 50 divided by 2, which gives us 25. Or again, you can use your calculator and type in this, and it'll give you 25 as well. So then when we do -2, now we would be dividing by 2 again. So then this one is going to be 25 divided by 2, which is 12.5. Or again, 50 times 2 to the -2, which would also give you 12.5. Number 7, here's an inequality. 3x plus 1 is greater than 34 minus 4x. Graph the solution set. So we're going to need to solve this for x first. And you can do this a couple different ways. You can turn this into an equal sign and solve for the equality, and then plug in values to figure out where your shading goes. You can also leave it as the inequality. And then if you multiply or divide by a negative number, then you need to make sure you flip the sign. So you may have figured out that pattern. You may have been taught that pattern. I can kind of show you both ways here. So I'm going to add 4x to both sides to get our x's together. So we're at 7x plus 1 equals 34. Then the 1 and the 34 are like terms, so I'm going to subtract 1 from both sides so that this is 0. So then I just have 7x equals 33. If 7 times x equals 33, we undo that multiplication by dividing. And so then we get that x equals 4.714. So that gives us where our dot goes. And then we know that it started without an equal sign underneath. So it started without that line. So this is going to be an open circle at 4.7. Then we just need to decide which way we shade, and that's by plugging in a number to your original equation. So I'm just going to choose to plug in 0. So I'm going to plug in 0 here so that I get 0 plus 1 is greater than 34 minus 0. So right now what it's saying is 1 is greater than 34, which is false. So that means that 0 is not in my shaded region. So I'm going to shade above the 7 point, or the 4.7. So that's one way. You could also have left this as a greater than sign. And so you could, leave that as a greater than sign. And right here, when you divide, you divided by a positive number. So you don't flip the sign. So then it just stays greater than. So we know that the solution is x's that are greater than 4.7, and greater is shading to the right. Number 8, here are the equations that define three functions, f of x, g of x, and h of x. Which value is largest when we plug in 100? So for f of x, we get 4 times 100, which is 400, minus 5, which gives us 395. For g of x, we get 4 times 100 minus 5 is 95. And 4 times 95 is 380. And then h of x, or h of 100, we'd be doing 100 divided by 4, which is 25, minus 5 gives us 20. So the largest value here is f of 100. B, which value is largest if we plug in negative 100? So if we plug in negative 100 to the f function, we're going to get negative 400 minus 5, which is negative 405. For g of negative 100, we're going to have 4 times negative 105, which gives us negative 420. And then h, we're going to be at negative 25 minus 5, which gives us negative 30. The number that's largest is the one closest to 0. Well, furthest to the right on the number line, and that's negative 30. So negative 30 is our largest. And then for part C, plugging in 1 over 100. So if we plug 1 over 100 in, we're going to be at 4 over 100 minus 5, which if you use your calculator is negative 4.96. G of 1/100th is going to be 4 times 1 over 100 minus 5. If you use your calculator for that, you get negative 19.96. And h of 1 over 100, so if we do 1 over 100 divided by 4 minus 5, we get negative 4.9975. So which of these is the largest? So again, which one's furthest to the left on the number line? And that's going to be negative 4.96. And not furthest to the left, furthest to the right. I don't know why I keep saying that. So furthest to the right. So if we did this, negative 19.6 would be like way down here, close to negative 20, right? And then you've got negative 5, and we've got negative 4.9975 would be here, and negative 4.96 would be here, furthest to the right. So that one's the largest.